This is the close-up of the real-time clock I wrote borrowing some software from a few other sketches that I found useful. It does use the real-time clock module that is highly accurate using the DS3231 chip. And when the Arduino is powered up, it retrieves the data as well as the temperature and then formats it for display. So very, very nice chip. It also, as I said, has the temperature available, which I've converted to Fahrenheit and have displayed on the screen here. I've got the digital and the analog display. And the way the sketch, most of the demo sketches are written for this particular library and chip are written, you have to use the serial port to initially set it. And I found very few sketches that actually have any kind of menu system that allows setting it. So using this 128 by 64 I2C display here, I have implemented a menu system that allows setting the clock from a series of 2 push buttons that I have wired in. The first one selects the mode, the setting mode, and that's done by pressing, and individual presses toggle the mode or the field that you're going to set. And the second button, for all modes except the second mode, actually, if you hold it down, will increment the value at a 5 Hertz rate until the desired value is reached. So that makes setting this quite convenient. So if I press and hold the set mode button, you can see I'm in the day of week mode. Now the month, the date, the year, hour, minute, second, and then back out to normal mode again. As you change it, the display gets updated dynamically, so the analog display, as you'll see in a second when I demonstrate it, will immediately show the effect of the setting. So let's just do that. So if we go to the day of week mode, I'm pressing and holding the set button, and that at the 5 Hertz rate will step through it. And you can see that gets updated immediately on the, well, doesn't it get updated because the day of week's not shown. But the hours, minutes, and seconds will. So we'll set that back to Sunday. You can see that wraps at the end of the week. Move on to the month. You can press and hold that to scroll through the various months. Again, wrapping at the end of the year. Likewise, for the date, I can press and hold that, and that will increment at the 5 Hertz rate, or I can do individual presses to step. I only go upward on any of these settings. I didn't add another button to go down. It didn't. The update rate's fast enough that it didn't seem necessary. One thing I found is that you can set illegal time combination or illegal date combinations, and the chip will accept them. So, for example, if I go to February, oops, missed it. I can set a date of, for example, February 30th, which of course never occurs. And the chip will gladly accept that. What will happen is that it'll continue. The chip will continue to increment the date at midnight until it wraps over to the 1st, and then thereafter it'll automatically catch the correct number of days in the month. But initially you can set it to the incorrect date. I don't know why you'd ever do it, but it's possible, and it's just a little glitch in the chip you should be aware of. I could have caught it in the software, but it didn't seem worth the effort. The RTC chip will actually handle dates starting at 1900. In software, I limit that to go between 2000 and 2099. It didn't seem to be of much value to maintain support for anything earlier than that. So you'll see as I get to 2099, it does wrap around. There you go. So you'll find when you first hook up the RTC chip, it defaults to the year 1900. The software doesn't care. It'll happily increment that until it hits that 2000 boundary or 2099 boundary, and when it wraps, it will wrap back to 2000 rather than the supported 1900 date. It does have a temperature display on there. Normally the chip updates the temperature once every 64 seconds. I didn't like that, and so I wrote in the code to initiate a temperature, what they call a temperature conversion, every 200 milliseconds if possible. And I do check the busy flag in the chip, so I don't try to initiate a new temperature reading until the previous one is completed, which is recommended by the datasheet. A side effect of doing that frequent conversion is that the real-time clock calibration is updated several times per second, so that should result in a much more accurate clock than if you just allowed the built-in 64-second default temperature update to take effect. It also allows very rapid updates of the temperature. I have my finger on the sensor now, and you can see that updates almost instantaneously. Temperature does seem to run a little bit high, but I think that may be because of heat being generated on the board. There is a small sensor next to the chip, or it may be integrated in the chip. I'm not sure which. So just to demonstrate the time setting function, you can see if I update that, I'm using a 12-hour time system with AM and PM indicators. Actually, the chip can operate in a 12-hour mode, but I left it at 24-hour mode, and I'm doing all of the adjustments to 12 hours in software. So all those conversions are being done there. It just seemed a bit more straightforward to do. You can see as I update the hours, the hour hand on the analog clock updates also. Likewise for the minute. And then on the second, as I press and hold it to reset it to 0, you'll see the second hand also immediately clicks back up to that 0 setting. So all the menu system worked out quite nicely, and makes it a lot more convenient to set it, and also makes it possible for a normal end user to set it who wouldn't have the Arduino IDE or a means of setting it through the serial or USB port. So this is the very basic clock. I have created a couple of kind of interesting enhancements for a Christmas gift for my two daughters. So I'll demonstrate that in another video or another part of this video. This version of the code is essentially identical to the one I showed for the generic clock, but I've added some animations of the Pusheen cat character that my daughters really liked, and I added a little dedication screen to display a little message periodically. So I've got, I'll plug it in. I apologize for the overexposure of the video. I had to do that to make it show up here. And there is the protective film there. That cloudiness you see on the edges is from the film. The update rate is fairly fast, every 200 milliseconds, which is adequate for a simple animation that I included on here. You can see I've got the dedication screen, and then it shifts periodically into a display of the little cartoon character in different poses, along with the analog clock shifted over to the right. But the everything else is identical. The setting modes and everything else work exactly as before. So I had some extra code space, so I thought I would add this in. So we'll just let that play through the various animations. You can get a feel for the sequence. I think the whole sequence takes about 5 minutes to run through with the different images. I did find I had to put the images on a light background on the OLED display to get it to look right. If I used reverse video, it just didn't look like the character, and it's pretty blocky as it is, and that just made recognition a little harder. So it looks a lot nicer with the white background, so I left that as it is. I do have code for the generic clock and also the Pusheen version. It does include the personalization screens, but those can be easily removed in the code with a couple of simple modifications. The display actually looks a lot better than you would guess from this demo. I had to overexpose it to stop the flickering caused by the frequency of the screen beating with the camera frequency. So it looks a little washed out, but it's actually extremely bright and clear on these little displays. These displays run for about $6 or $7, I think, if you shop around on eBay from a US-based source. And they're very, very tiny, and they make a real nice display for an application like this. I did add at the center of the analog clock a little flashing activity indicator circle that flashes at the display update rate, actually half the display update rate, and that just gives an indication of the display updating correctly. What kind of interesting effect of the set button, if I press and hold the mode button to enter the setting mode, can set it to any mode. As long as I hold it down, it enters a loop waiting for the button to be released, and that essentially freezes the display. So you can kind of freeze what you're seeing if you want to look at it. When you let it go, the clock updates. You can see the second hand jumped ahead here when I did that. I'll show it on the animation. It's a little clearer there. There we go. If I press and hold it, it freezes one of the frames, and I release it, and it just picks up where it left off. It has absolutely no effect on the time setting or the temperature functions. They update immediately when the button is released. So just a little feature, I suppose, associated with that. So that's it. Kind of a nice little animated display that builds on the DS3231 chip. Very nice. This video just shows an overview of how I have things hooked up for the clock. This is the real-time clock module. The display is over here, and both of those use the I2C interface. So all that's necessary is to daisy chain power and ground, which is done here by these wires, to both of the modules. And the two necessary clock and write pins and data pins from the I2C pins on the Arduino are then connected to the module and then paralleled over here. The module and the display have different addresses, so it's possible excuse me, to operate those in parallel without any difficulty. Here you can see the two buttons I've got hooked up to ports, or pins 8 and 9 on the board. You could change that to be whatever you want it to be. So this is the basic breadboard system. I'm going to use the code on an Arduino Pro Micro, which is about half the size of this Arduino Micro, and also less expensive, and then just sandwich the real-time clock board on top of the Arduino and then add the display on the front. So the wiring is actually quite minimal for this. Two switches here add almost as much complexity as adding the communications interface on the rest of the circuit. You can see this button toggles the modes on the clock display, and the other button, if I hold it down, will walk up or scroll through the various valid settings for that field. So works great on the breadboard, and I anticipate once I get this packaged up, it'll be kind of a nice little Christmas gift, little stocking stuffer for Christmas. The actual real-time clock chip, let's see if I can get it to focus here, is here. The large surface mount chip is the clock module. The module also has a separately addressable 32K double EEPROM on it. So you could use this to store any kind of data for like data logger applications or other purposes. I'm not using that at all, but it is available, and there are libraries out there that can address it. So the two chips are essentially completely independent. The temperature sensor is one of these chips down here, probably a diode of some type. It could be the one on the top, but it seems more sensitive when I get my finger near it here. There is also a square wave output, the second pin down on the connectors. I do have the code configured to output a 1 Hertz square wave that's calibrated to the internal temperature compensated oscillator. And I've read some reports on the web that 1 Hertz output signal is, the rising edge of it, if you use it to synchronize other devices, is quite accurate. So I do have that enabled in the software if you would care to use it. Those other pins could be used for other functions. There are alarm functions on the chip as well, the DS3231. I'm not using any of the alarm functions, but you can set those up to trigger different outputs on the excuse me, on the square wave output here. On the back of the board, this particular version of the module comes with a lithium battery. At first I thought it was a CR2032 lithium cell, but it's not. It's actually an LAR2032, which is a rechargeable lithium ion battery. And when connected to power, there is a charging circuit on the board that will keep this battery charged. So it should never need replacement, theoretically, and once fully charged and the power to the circuit is turned off, it should maintain time for up to a year on a charge without applying power again. But once power is applied, that battery does charge with automatic cutoff. So that is a really nice feature of the board. The battery is a little bit bigger. There are versions of this board that have a smaller lithium battery on it, but they tend to cost a little bit more, and it does add some thickness to the module. But this version seems to be a bit cheaper, so that works out okay. Some of the connections for the I2C port are also duplicated on the other edge of the board, which is kind of nice. I did verify the square wave output is outputting correctly using an oscilloscope, so the code is properly setting that up. And so all in all, for the price, it's a great, very, very accurate. The claims are, I forget the parts per million, I think 2 to 3 parts per million, which equates to a year-long accuracy of about a minute. So the clock should not drift. The temperature compensation from the built-in thermometer really seems to take care of that quite well, and there's some studies where people have analyzed this in detail, comparing it to a GPS source to determine the accuracy. And the claims, even on these Chinese source devices, seems to be quite good. So the chips seem to be genuine, even from China sources, and all of the temperature compensation and everything else does seem to work correctly. So my guess is the reason they're so inexpensive is they're from some build overrun or some other gray market source for the parts. But for whatever reason, they do seem to work well. I've tested 3 or 4 of these, and they all seem to have very comparable performance.